independence. So what we know so far is sample space, an event, a complement, a union, an intersection, the empty set, the axioms of probability, and all of these rules that we've come across just using the rules of probability. And then we came up with this idea of conditional probability, and we know that conditional probability is not symmetric. So what we want to do is continue on this idea of conditional probability so that we can think about situations where maybe it doesn't matter. And that's basically the idea. So here we know conditional probability. If we're interested in the probability of some event, F, given E. Remember, we know the outcome is in E has occurred. We just want to see where they match up and then divide by the probability of E. Now, this additional information changes the probability of F, as we've seen in our previous video. But what if it doesn't? That's the big thing, because that need not be the case. It may not always change the probability. So what if the probability of F given E is equal to the probability of F? E had no effect. And the probability of E given F is equal to the probability of E. F had no effect. Well, in this case, we would say that these are independent events. And they're independent if and only if this is true. And both conditions have to hold. So if I ask you to do something like this and you only show one, you're not getting it correct. You have to show both actually are satisfied in order for this to work. Now, this is an extremely important idea for later, because often when you take in statistics classes in the past, they've talked about, oh, well, you want things to be independent, but often they don't tell you what that means, and they mean it in a probabilistic sense, that knowing the outcome of one has no influence of the probability of the other outcome, or the probability of any of the values of the other outcome. So we got to keep this in mind. With a little algebra, you can play with this, and you can see that the probability of F intersect E is equal to the probability of F given E times the probability of E. Now, this is true whether or not they're independent. But if they are independent, then we can substitute this, right? Because we know that the probability of F given E is just the probability of F, which means we get the probability of F intersect E is equal to the probability of F times the probability of E. So if they're independent, then this holds, which makes calculations a whole lot easier if things are independent when trying to find the intersection. Now, notice this only holds if they're independent, and often people will assume things are independent when they're not. So be very careful when you do that. All right, so here's a quick example. I have lots of forensic scientists that I talk with. Suppose at a crime scene, there's a probability that blood is present is about 0.126. So there's about 12.6% chance that I'm going to show up at a crime scene and there'll be some blood someplace. I'm a squeamish person. That's why I care about this, because I will get sick if I showed up to that. So what's the probability that one goes on two independent crime scenes and both have blood present? Okay, so is it just 0.126 plus 0.126? No. So here I'm interested in blood at both. That means there's going to be blood at the first intersect blood at the second, which is the probability of blood at the first times the probability of blood at the second. And notice that's because they're independent. So that's 0.126 times 0.126, which is equal to 0.15876. So notice this number was probably smaller than what you were expecting just initially off your head. Like, okay, well, that's only 1.5% of the time that would actually occur at both of them. Okay, so now we've added this additional rule here. We actually added two additional rules. We added this rule and we added this rule to our list of all of the rules that we've been doing. And we're making our way towards Bayes' theorem, which we're getting very close to being at. So just hang on, and then once we hit Bayes' theorem, we'll be able to actually start doing some Bayesian statistics. But if we don't have Bayes' theorem, we really can't talk about it. All right, so we'll move on to, I think, the law of total probability in the next video, and I'll see you there.